This is Physics 104B at Porterville College, Chapter 26 homework, starting with number 17. We're looking for the magnitude of a magnetic force on a proton given a speed and various directions with the magnetic field. Here's my picture. We have part A going perpendicular, part B at a 30-degree angle, part C going parallel to the magnetic field. We'll use the equation F equals QVB sine theta. And so for part A, there's the charge of a proton Q times V times B, and then times sine of 90 degrees will make this force maximized. 2 times 10 to the negative 14 newtons. Part B, we just make it a sine of 30 degrees, and it's 1 times 10 to the negative 14 newtons. Part C, the force is 0, with that theta angle being 0 degrees. Number 19, velocity selector. We talked about that in class, and it describes it in the book. There's the magnetic field, there's the electric field. What speed will the charged particles go through undetected? This is where the magnetic field and electric field are equal and opposite in direction. So QVB for the magnetic field equals QE for the electric field. The Q's divide out, and we're left with V equals electric field over magnetic field. And you should get 4 times 10 to the 5th meters per second. Number 20, find the radius of the path of a proton with its speed 15 kilometers per second in a plane perpendicular to a 400 Gauss magnetic field. We'll say F equals ma, so the force is QVB equals ma, and for circular motion, ma becomes mv squared over r. So we'll take this equation, QVB equals mv squared over r, solve it for r, and we get the radius of the path is mv over qb. Remember that 1 Gauss is 10 to the negative 4 Teslas, so that's going to be 400 times 10 to the negative 4 Tesla. We've got the mass of a proton. We've got the charge on a proton, and you should get a radius of 3.99 millimeters. Number 21. How long does it take an electron to complete a circular orbit? Okay, this is similar concept to the previous problem. In the previous problem we solved for radius is mv over qb. We've got this here, we're solving for period. So period is 2 pi r over v. So what I've done to solve this, you might choose another way algebraically, but what I've done, recognizing that I want r over v, I took this equation and solved it for r over v. So dividing v into both sides, I get r over v is m over qb. And with r over v being m over qb, I come to the period equation and I say period is 2 pi times, and here's that r over v, m over qb. Now we plug in the values. Here's the mass of an electron, the charge on an electron, and we get 360 nanoseconds. Okay, for number 26, we have a wire carrying a current, makes 25-degree angle with a uniform magnetic field. We're given not the force, but the force per unit length, 0.31 newtons per meter. So we want to find the field strength and the maximum force that could be achieved. All right, so here's my diagram right here with that angle theta. And if we have F equals ILB sine theta, we solve that for magnetic field, F over IL sine theta. And we're given force per unit length. So we're going to put in the numerator that we're going to take this F over L and put F over L in the numerator. So it's force per unit length divided by I sine theta. And that gives us 49 millitesla as the answer. In part B, we want to know what could the force per unit length be maximized, and that would be where the angle theta is 90 degrees, so the current goes perpendicular to the magnetic field. And so we'll take F over L maximized is IB sine theta, or sine 90 degrees, which is just I times B, and we should get 0.73 newtons per meter. Number 28, we're dealing with a wire running horizontally at right angles to a horizontal magnetic field, and it is suspended against gravity. What is the magnetic field strength that can do this? I have a force diagram here, and we'll have the, first of all, here's my diagram of the horizontal wire in a horizontal magnetic field. You can use the right-hand rule to see that the current going that way relative to the magnetic field, your right-hand rule is going to make the force be upward on the page. And so here's my force diagram. The magnetic force, ILB, going up, and mg, the weight of the wire, going down. So ILB equals mg. We solve for magnetic field. B is m over L, that's the mass per unit length, times g over current. We are given the mass per unit length in the problem, times g divided by the current, and I get 0.12 Tesla. Number 33, standard household wiring. Parallel wires 1 centimeter apart carry currents of about 15 amperes. What is the force per unit length between these wires? Go back in the book, you can find its equation 26.11 that gives, for this situation, the force between the wires is the mu naught times the product of the currents times the length over 2 pi over their distance. We want to know the force per unit length, so let's divide both sides by length, and we have force per length is mu naught I1, I2, 2 pi, and the distance. And we get 0.0045 newtons per meter. Number 35. A single turn square loop wire, square wire loop, 5 centimeters on a side, there's its current. What is the loop's magnetic dipole moment? Alright, we'll start with that question. Magnetic dipole moment is current times the area in the loop, and so we have 0.45 amperes times 0.05 meters squared, and we get 1.1 times 10 to the negative 3 amperes meters squared. Question B asks what is the magnitude of the torque that it experiences. Torque is the dipole moment times the magnetic field, the cross product of those vectors. We want to know the magnitude, so it's going to be mu times b times sine theta. We solved in part A the dipole moment. I've got it more specific here. Instead of just, in part A, I just gave the answer of 1.1. But let's take it out all the digits. 1.1125 times 10 to the negative 3 amperes meters squared times the magnetic field of 1.4 Tesla, and it says it's oriented with an angle of 40 degrees, so times the sine of 40. And we get 1 times 10 to the negative 3 newtons meters. Number 42, a particle carrying 50 microcoulomb charge. It gives its velocity, it gives the magnetic field. Find the magnetic force, form the dot products to show explicitly that the force is perpendicular to both V and B. All right. Force is QV cross B, which is Q times V cross B. And we set up a cross product by doing the determinant, or this is the way I've taught in class, the determinant of the matrix, where the first row is I hat, J hat, K hat. The second row is the three components of the velocity vector, and the third row is the three components of the magnetic field vector. So when I plug in those values, it becomes this matrix right here. We take the determinant, and remember, for a 3 by 3 matrix, you'll start on this row with I hat and the determinant of this 2 by 2 that excludes the I hat. Then minus J hat times the determinant of, I'm going to cover this column up, the determinant of the 2 by 2 that excludes the J hat. So 5 times 0 minus 3.2 times 9.4. Remember that you started out with a minus J hat times that, so the minus and the minus will actually make that a plus. And then finally plus K hat, and I'm going to cover up the column, and it's going to be times the determinant of this 2 by 2. 5 times 6.7 minus 0 times 9.4. When you do that, oh, and also we're multiplying by Q. Don't forget you're going to do Q times that entire determinant. So in the end, we get this as the force vector. You might want to reduce that to millinewtons, but I have it in newtons, so negative 0.0011 in the x direction, 0.0015 in the y direction, and 0.0017 in the z direction. The next is show that each dot product equals 0. That's effectively what it's asking. Form the dot product of FV and FB to show that force is perpendicular to V and B. So the dot product, to show that they're perpendicular, the dot product should be 0. Now I've only done this for F and V. You can do it separately for F and B. But as I form the dot product, that's Fx times Vx plus Fy times Vy plus Fz times Vz. So you plug in those numbers and you get that it's 0, and that means that F and V are perpendicular. And you can follow the same steps plugging in the x, y, and z components for the magnetic field, and you should get the same result, that the dot product is 0. Number 44. I've done this on 2 separate pages. One of them is just looking at the vectors and how we treat vectors mathematically. And on the second page, I will look at using the right-hand rule to find direction. And so just keep in mind there's a second page coming up that treats this problem a little differently, and maybe you want to skip ahead to that second page. But here it is, number 44. A proton, there's its velocity, there's its magnetic force. A second proton on the x-axis, that's an important part there, moving on the x-axis, experiences a magnetic force given. Find the magnitude and direction of the magnetic field and the velocity of the second proton. So here's my solution. We have V1, we have F1, F equals QV cross B, and so we have, here is QV cross B, which is the determinant of the matrix, where I've got the V vector and I've got the B vector. The B vector is unknown, and so I just call it Bx, By, and Bz. When I do this determinant, I end up with, for I hat, 3.6 times 10 to the 4th Bz times Q. For the J hat goes to 0, there is none there, and for the K hat it's minus 3.6 times 10 to the 4th times Bx times Q in the K hat direction. This is the force vector. Let's relate it to the force vector that is given. So here's the force vector that's given, and it equals the QV cross B that we just solved for. And we can see that just looking at this Z component right here, 0 equals negative 3.6 times 10 to the fourth bx times q. Well, what this tells us, since this isn't 0 and this isn't 0, that bx must be 0. So we know that bx is 0. This second row, we're working backwards up the matrices, or up the vectors. This second row tells us nothing, just that 0 equals 0. Let's go up to the first row. 7.4 times 10 to the negative 6 newtons equals 3.6 times 10 to the fourth bzq. And so you can solve for that and get what bz is. Now, for q, it says it's a proton, so we plug in the charge of a proton. And you should get that the magnetic field then is 0.128 Tesla. Now, that is in the z direction. Let's go up here now. We now look at the second proton. So the velocity of the second proton is, and it says it's moving in the x direction. I'm sorry, it says it's moving along the x-axis. So we don't know whether that's negative or positive, but it's only got I hat components. So we'll just say the velocity vector of the second proton is v times I hat. We know the force that it feels. It's in the j hat direction. And so we can do for this proton, q v cross b, and here we have once again q times the determinant of v and b. And we know that that's going to equal the force. And so here's the determinant that I'm going to calculate. Here is the force vector that's given. So in the middle, I'm going to solve for that determinant. When you solve the determinant, it gives I hat, 0, 0, that goes away, minus j hat, vbz, minus that, and k hat, which is vby minus 0 and times q. So the k hat direction is going to equal 0, and that means that by is equal 0. And we have q vbz j hat equals 2.8 times 10 to the negative 6 newtons. Now, what this tells us, once again, basically all we got here, the important part that we're getting was that by is equal to 0, because previously, if you go up the page, we had solved for bx and bz. We don't have to solve for those again. We already know what those are. We were just looking for what is by, and that equals 0. So that just gives us that our magnetic field is, in fact, here's the x component, the y component, and the z component. So 0.128 Teslas. You know, I'm just realizing, excuse me, let me go back. This is actually a minor point here, but sorry about this. As I did the j hat, it needs to be minus v times bz. That should actually be a minus sign in there. It's not going to affect what we did here, because all we were looking for was by equals 0. And how that does change, it doesn't really change anything, but it's actually, it has something to do with which way the v vector is. We still haven't determined is that positive or negative, but that negative sign there is giving a little insight into that. So sorry about that little mistake, but the point was getting what by is down here, and that equals 0. Okay. So now we have then that F2 is QVB, which means that the speed is F over QB. Now this is just the magnitude of the speed, and it's 1.4 times 10 to the 4 meters per second. Okay, I told you that there would be another way that we would look at this problem, and so this way is more visual and less mathematical. Okay, it would be good, rather than just dealing with vectors like I did on the previous page, dealing with the math, let's more conceptually, visually think about which way, what direction things are going. So we have that in number 44, the proton is moving in the positive J direction, as I've drawn it. And it experiences a magnetic force in the positive X direction. We can use the right-hand rule and show that if it's going up on the page and our thumb points to the right, then the magnetic field is curling out of the page. It's coming out, so it's in the positive Z direction, meaning there's no X component, there's no Y component. We went through several vectors on the previous page to figure that out, but here we just have it using the right-hand rule. It's only in the Z direction. And then we can say QV1B is equal to the force on 1, so the magnetic field is F1 over QV1. Then we can use the right-hand rule for the second proton. Now that we know which way the magnetic field is, it's coming out of the page, the force is up, so I'm going to use the right-hand rule. My fingers are curling out of the page, my thumb is pointing up, and when that happens, my arm is pointing to the left, which tells us that the second proton, while it is moving along the x-axis, it's moving in the negative x direction, in the negative direction. And we can do V2 equals F2 over QB and get that it's 1.4 times 10 to the 4th meters per second. So, two different ways of solving that problem, and I think the second page is a lot easier than the first one with the vectors. Okay, number 45, this is the last page. Number 45, a simplified model of the Earth's magnetic field has it originating in a single current loop. So we're going to pretend, we're going to imagine that the Earth's magnetic field is caused by simply a wire loop going around something like the size comparable to the Earth at the outer edge of the planet's liquid core, radius 3,000 kilometers. If this were true, what current would give the 62 microtesla field measured at the north magnetic pole? All right. So we have the radius of our imaginary loop, we have the magnetic field, we have X, and we got this equation. This is from example 26.3. You should review in the book or the notes that, so you don't have to derive through it again, but it's the field of a current loop, and its magnetic field equals, we have the permeability constant mu naught, times current times a squared, where a is the radius of the loop. X is the direction. X is the distance from the center of the loop to the pole, which is essentially that's going to be the radius of the Earth, 6.37 times 10 to the 6th meters. And we take this algebraically. We solve it for I, the current. It gives 2b times x squared plus a squared to the 3/2 power over mu naught a, and you should get 3.8 times 10 to the 9th amperes. So it would be a nearly 4 billion ampere current in a loop the size of the Earth's liquid core that would cause such a magnetic field. Number 50. A wire of negligible resistance is bent into a rectangle. The right-hand side of the circuit extends into a region containing a uniform magnetic field pointing into the page. Find the magnitude and direction of the net force on the circuit. So as you look at the diagram, we have that the current is going around. It starts at the positive terminal, goes through and down up into the negative terminal. You can use the right-hand rule and find that the magnetic field on such a current that's going down the page is being forced to the right. Now, let's look at the other four parts of the loop. This part is not in the magnetic field. It's not getting any force. This part and this part, the top and the bottom, the parts of them that are in the magnetic field, they're going to be equal and opposite. They're actually going to cancel out. You can use the right-hand rule to find that the one on the top is going to get forced up. The one on the bottom, because of the opposite direction of the current, it's going to get forced down. So top and bottom, up and down forces are going to cancel each other out. The only force, net force, is going to be this wire being pulled to the right. The force on it is IL cross B. It is perpendicular to the magnetic field, so that's ILB times sine theta, which is just ILB. The current is the electromotive force, that 12 volts from the battery, divided by the resistance, 12 volts divided by 3 ohms, times the length of the wire that's in the current, and it says 10 centimeters, so 0.1 meters times the magnetic field, and you get 0.0152 newtons. The last problem, number 59. A small piece of wire carrying current I is bent, so it includes a circular loop of radius A. Find an expression for the magnetic field at the loop center. The magnetic field, we'll use the superposition principle that the field vector is the field from the straight wire plus the field from the circular loop. And we are looking for the magnetic field at the center of the loop. The loop has a radius of A, and so at the center, the field from the straight wire is mu naught I divided by 2 pi times your distance, which is A. And we can also find, using the right-hand rule, that given the direction the current is going, that it's going to be coming out of the page. This is the right-hand rule, where you act as if you're grabbing the wire with your right hand, your thumb points in the direction of current, and your fingers curl around the wire in the direction of the magnetic field. And in the above the wire, that's out of the page. Now, the magnetic field produced by the loop at the center of the loop is given by this equation from example 26.3. I'll zoom in a little here. Okay. And it's mu naught I A squared over 2 divided by, this equation is, this expression right here is x squared, your distance along the axis of the loop, but you're right in the middle of the loop, so x becomes 0. And this a squared to the 3/2 power just becomes a cubed. And you can use the right-hand rule for a loop, and you find that it is also out of the page. When we simplify these two expressions, we get mu naught I over 2 pi a plus mu naught I over 2 pi a. They're both out of the page, so they add to each other. I'm sorry, I think I misspoke a few seconds ago. This is mu naught I over 2a. So this is the answer, but let's simplify it a little bit. We can factor out mu naught I over 2a, and we get 1 over pi plus 1. We can also simplify, these are all just different ways of stating the same expression, mu naught I over 2 pi a times 1 plus pi. And that concludes the chapter 26 homework.